There is an ever-growing wealth of mathematical models which are formulated and used to describe phenomena in the chemical and biochemical sciences. We must therefore confine ourselves here to a special case, namely deterministic models to describe time-response relationships. An important subclass of these are growth phenomena, be it that they are concerned with the growth of a biological entity, such as the weight or size of an animal, or with the growth of a concentration in a chemical reaction, or others. Most of the mathematical models that are invoked describe growth or time response in general as arising from differential equations. Let us describe how such an equation arises in a very simple example. Here then we have an example of a response which I have denoted by a concentration and the time at which the process is running. We first assume a model that is an idealized theory for the differential growth of, say, this concentration of a particular chemical in a reaction. Y sub t denotes the concentration of this chemical at time t. Y sub t. And we may, in certain cases, make the following assumptions. We assume that the concentration will eventually reach a stable level, capital Y. It will grow, in this case, to a stable level, beyond which it cannot grow. Assumption number one. Assumption number two. At any time of this growth development of the concentration, the differential increase, that is the slope of the growth curve, is proportional to the what I call dilution. That is the difference between the concentration reached and the final maximum concentration. So the slope is proportional to the distance from the asymptotic line. Expressing these assumptions in mathematical terms, we obtain the differential equation here. Growth rate, dy dt, proportional to the distance between y, that is this level, and the concentration reached at time t. C times dilution. Very simple. The solution of this differential equation is this very simple exponential law. When t is 0, the exponential is 1, y cancels, and we have y sub naught, the initial concentration. When t tends to infinity, this term is 0, and we approach the final concentration, capital Y. This is the exponential growth curve, sometimes in agronomy referred to as Mitscherlich law. You need a towel to pronounce Mitscherlich. I shan't even write it down. At this stage, you may have two remarks. You may rightly consider the assumptions about the differential growth rate a gross oversimplification and possibly inapplicable. Secondly, you may wonder why a high-speed computer is needed to evaluate the resulting growth curve in their simple form here. There's a close relation between the answers to these two questions. A more realistic formulation of a model for differential growth of these concentrations will usually involve not just one variable as that single concentration, but simultaneous measurements on different facets of the process. For example, in describing a complex chemical reaction, the growth in the concentration of each particular chemical involved, each particular chemical component, will in turn depend on the concentrations of the other components, on temperature, and many other variables, which should all be entered into the model equations, into these equations. Such a model would then involve sometimes as many as 30 to 50 or even more variables and differential equations for their respective growth rates in place of a single equation too, the single equation here. Moreover, a simple assumption that the effect on the growth rates of all these concentrations is given by a linear relationship is often regarded as unacceptable. When we now face the mathematics, so I like to display a more general model. Here it is. This is a vector, say, of concentrations. dy dt is therefore a vector of growth rate differentials equal to a vector function f, and that vector function depends on the non-linearly on the elements of all the elements of the vector y, and also on unknown parameters, possibly theta. So this is the law that the model that you more realistically should be formulating. When we now face the mathematician and ask him to solve the equations for our more realistic model, he will no longer be able to do this by mathematical analysis. A system of nonlinear differential equations, it's lucky if you can do it. This means you will no longer be able to produce an equivalent to the simple equation that we had here, expressing the answer for the vector y as a simple function of the time t, no longer possible. However, a high-speed computer can still solve our complicated system of differential equations numerically or graphically and produce the equivalent to the growth curve. Numerical answers can still be produced directly from the differential equations without having the mathematical solution. To the chemist, or to the computer expert, this task is known under the name of solving a system of ordinary first-order nonlinear differential equations, which can be easily done on the computer. You probably know of computer programs that will do that. To the chemist or biochemist, this means that he is now much freer to formulate his model, that is his theory, and formulate it more realistically, for he does no longer rely on whether or not the mathematician can provide the solution in the form of mathematical equations. He can now incorporate in his model for differential growth all relevant components and all variables he deems worth incorporating. He can experiment with the variables he wants to include. He can experiment with the model form in which the various variables affect the differential growth of any of the variables. He can follow up certain hunches, discarding theories which do not tally with observations, and improving promising theories by putting them to a more searching test. And here I'd like to intersperse, if the differential equations depend on a set of unknown parameters, theta, a vector of parameters, you can still fit these solutions to the differential equations by least squares. Observed vectors of observations, capital Y, can be fitted by least squares. minimizing the familiar least square forms in non-linear least square estimation theory. All operations that are known in this technique that are based on an analytic knowledge of the solution for your model can be simulated numerically by using numerical solutions to the differential equation, including differential changes in the parameters, if they are needed. The so-called method of solving the system of differential equation by perturbation is extremely serviceable. For example, the modified Gauss-Newton method of solving nonlinear least squares problem can immediately be done even if you don't know the nonlinear form of the solution of differential equations. There is, as many of you will know, essentially nothing new in this application of high-speed computer. Possibly this last remark is. Indeed, it has been used in many areas of research. To name only a few: the study of enzyme reactions, the development of a theory of nerve circuits and responses, explorations of the responses in the output of chemical plants to systematic changes in controllable factors. The future will produce bigger and better computers, and with their aid, we can be both bolder and at the same time more realistic. Yes, both bolder and more realistic in the formulation of our theories. For we have a tool which will evaluate for us accurately and timely the consequences of a great variety of theories, and thereby provide most valuable pointers to the ingenuity of the scientist. Thank you.
Thank you, Dr. Hartley. Are there any questions that anybody from the audience would like to ask him? Yes.
Somebody's got to trigger this process. Say, I think that I was wondering whether you really weren't making the case against the difficulty of Monte Carlo rather stronger than it should be in giving this Kolmogorov-Smirnov result. In that, at least in the statistical inference game, one really doesn't need to know these distributions so well. My view on this is that if one wants to use a certain method of testing, and the principle of optimality is the rather good one, that I like that one. The hell with everybody else. Perfectly good principle of optimality, providing one isn't being stupid. Then, so I want to know how this thing is distributed, and so I'm interested in dragging the upper tail a bit. Well, my advice is, just run off a couple of hundred samples, 200. That'll give you some sort of halfway decent idea of what the tail is, and that's good enough for your purposes, probably. Okay? Do you have any reaction?
I think you are right with regard to this. I think this discussion of the 10 to the minus 5 times 10 to the minus 4, 3 accurate decimals, was more addressed to the people who want to use Monte Carlo methods for computing tables of functions that are analytically not tractable. If you want to produce a table of a distribution criterion, let us say, in tables of biometric tables for statisticians, you would blame us, Kempe, unless we have something like 3 accurate decimals. And I was But I think you're absolutely right. If you just want to investigate a new criterion, you may well be satisfied with a much lower accuracy.
Paul, in your allusion to stochastic PERT, I don't know anything about it, but I've been on the fringes of it and curious about how the stochastic element really is introduced in that type of thing. Now, the standard non-stochastic network analysis assumes certain known times for task completion and then figures out the best route through the network to take who needs to wait for what, or at least this is my interpretation of critical path. Now, when you introduce stochastic elements, what does the planner work with then? Does
Yes.
it work with a distribution of completion times
Exactly.
at each station? But I fail to see how a critical path then could be worked out on a specific occasion if you don't have the information of how tasks are being completed on that particular day. What good is the distributional information?
There is no longer a critical path. But as you rightly say, we have programs for this written. We can put, you have a network. Let's write a very simple one, right? There is a distribution for the completion times of each of these tasks. This is a directed network. And the computer program computes from those distribution the complete distribution of completing the whole project to go from there to there. How does the planner use this? He may look at the expected value of this completion time. He may look at the upper 95%. That depends on his outlook. But this statistical PERT produces for him the complete distribution of the completion times for networks that are very sizable. This is not an easy distribution problem. Monte Carlo has been used to solve this, but we have a method of doing the job by numerical integration. It's a fairly sophisticated program, but there is no longer a critical path. A critical path is defined when you have definite completion times, and as you say, it is the one that takes longest to complete, to go from beginning to end. That's the critical path. This will no longer be applying because what is the critical path depends on the sample of completion times that you have drawn. So you have the critical path is now a statistic and has a distribution. But this is a method that can be tackled by Monte Carlo, but for many, the more benign networks, let me say, we have a numerical integration algorithm to solve the distribution problem. Takes a lot of computer time, but I don't know how. Go ahead.
One of the things I didn't hear you mention was, in regard to computers, was the speeding up the rate at which we can learn about behavioral relationships and analyze the data, particularly the low marginal cost of running added iterations and new specifications of models. It would seem that speeds up the rate at which new knowledge can be generated about behavior, especially like in the social sciences.
Well, I mentioned the importance of having social scientists in the business of using computer in conjunction with data editing. I did not want to imply that this activity would increase the knowledge of the social sciences, except that the data in the social research area have been edited again for errors, so so that the output is more reliable for the social scientist to use. Where the social scientist enters into the editing procedure is that he makes the very valuable suggestions as to what kind of errors do households make in responding about their characteristics. What are frequently occurring? You have to know a lot about how the head of a household responds, how his wife responds, how the children would respond, to various types of questions before you can talk about error pattern in the responses that are likely and others that are unlikely. I wouldn't like to guess this. If you are a social scientist, maybe you can help.
No, but that's not what I'm getting at. I'm saying that the marginal cost is running a new functional form, say a new model in terms of looking at relationships between dependent and independent variables and things like that.
Or the last example you were really more concerned with.
Yeah.
Yes.
That's right.
Well,
you can, if it's going to take you another year to invert a matrix in terms of running another regression, you may not do it if you had to calculate it by hand. But with high-speed computers, you can run many specifications with very low marginal cost, and this would seem to speed up the rate of advance of knowledge in these areas.
well, supposing you have a learning process, a model for a learning process, in, say, in animal psychology, right? You set up a model for what are the factors that affect the frequency with which the animal has the right answer, right? And goes to the right cage. Now, I'm sure that people start sensibly with very, very simple models. And unfortunately, they find the observations do not bear out these simple models. Now we rely on the ingenuity of the animal psychologists to suggest factors that the simple model had omitted. And as you bring in more and more and more of these, you may find that the model is so complicated that there is no mathematical analytic solution for it. But the computer can still solve it. Certainly in the case of a differential equation. I don't know whether a learning process can be described by differential equations, but here's an example then where the computer can still do it for you numerically. And numerical answers from the model is all you need to make a comparison with direct experimental evidence. Therefore, analytic solution is no longer necessary, and you do not need to restrict yourself to such mathematical models that can be solved analytically. That, I think, is a great boon.
A great boon, but with some dangers of just throwing in whatever occurs to you, and it may be counter-creative because the experimenter may not be sufficiently forced to think very hard about the processes involved. He throws in any idea he has. That's the danger of this, which of course can be minimized by a careful experimenter.
Yes, you are right, throwing in too many very thoughtlessly, which I couldn't yet judge if that a scientist does to me. However, Herb, the characteristic that a model is analytically tractable is often completely unrelated, in fact negatively correlated to whether it is a good model or not. Right? So in the past, people have selected models that were analytically tractable, and I think we get rid of that. Now, they may still be thoughtless and try to many things that are useless. The other Herb has it.
Well, I think a physicist would hate you for saying
You know, poet, beauty is truth, and truth beauty. That is all you know on earth. That's all you need to know. This mathematical stuff is beautiful.
Have the simple laws outlived their time, then?
I don't think
in
so.
regulation? Because they obviously are approximations.
I like to remind you that in conjunction with the Monte Carlo, I pointed out that the numerical solution to a problem that depends on a large number of parameters is really not adequate. And you need these analytic approximations to guide the numerical evaluation by Monte Carlo. Same applies to solving differential equations numerically that depend on a large number of parameters. Analytic solutions are a useful guide as to what you should be doing. They are sensible. So I don't think one should do away with it. I did not want to indicate that you should do away with them, but I am very much in favor to let the subject matter area scientist freely build the model on what he considers is important, irrespective of whether the thing is mathematically tractable or not. I think that is a boon, definitely.
If there aren't any other questions, let's thank
There's one down
Oh,
there.
there is, okay.
Just a comment. A peculiar twist on what you're pointing out is that psychologists no longer try to empirically verify Markov learning models because the computer solving these problems was estimated that in order to get a confidence interval for some of these transition probabilities, they would have to run 50,000 rats for 50 years. So that a whole research area that had been, quote, very productive, unquote, got undermined and was completely abandoned in the middle 50s, 60s because of it.
Because of the large number of
Animals
that are
evolved
needed when you are dealing with more complex models.
when they're dealing with Markov models. No,
Markov
the
models.
confidence interval for transition probabilities for some of these Markov models that were developed for explaining animal learning.
Leroy, is your point, I think I understand your point. You say there is a difficulty about involved models, not just that they are possibly not analytically tractable, but their monitoring, their verification requires unacceptable experimental programs. And you say that is a more important consideration than doing away with the
No, I'm saying that researchers have saved themselves a lot of time by the computer showing them that they could not possibly empirically support some of the theories they were advocating.
Oh, yes, I'm sorry. This is another point. You can use the computer to trace out a projection, of a theory and show that a theory is unacceptable because the consequences are quite unacceptable without even
The data you
invoking
need to support the theory.
experiments.
Rats don't live that long.
Yeah. Right? Yeah. In other words, you feel there's a use of a computer that I failed to mention, namely that they often are able to reject unacceptable theories by pointing up the unacceptable consequences. Yes, maybe I certainly didn't stress that enough. That's a very good use of a computer also. I think that has been done with genetic models, I believe. That certain models have been found quite acceptable. Maybe Kempe knows more about that. Some of these computer simulation of genetic processes have been implemented and found to lead to completely unacceptable consequences in the third, fourth, or fifth generation. Without conducting an experiment that produces so many generations.
Any other questions for Dr. Hartley? Let's give him another round of